This is Christopher Boucher, and I'm going to review how to do a hypothesis test using the z-distribution and solving it with the p-value method. Okay. Now I've already used this example for a rejection zone method example, but this one we're going to use the p-value, so the numbers will look the same to you. Okay. So I'll go kind of fast to the beginning because the numbers are the same as one of my other videos. The average annual salary for a starting plumber in the United States is $40,000 with a standard deviation of $500. A sample of 32 new plumbers shows an average annual salary of $40,200. Based on this data, are new plumbers earning significantly more than expected? Perform a hypothesis test at a 2.5 level of significance. Okay, so our null hypothesis is that the plumbers are earning at least $40,000 or less. That's the way this is set up. And that's because our alternative hypothesis is that they're earning more. Our mu is 40,000, which is our population mean. And our population standard deviation is 500. And we know that that is the population standard deviation because it's in the same sentence as our mu, which is our population mean. So that's something to consider, is where the information is provided. So 500. And then our x bar is our sample mean, which is 40,200. And our n, which is our sample, small n, which is our sample size, is 32. Okay, we'll do this too. We have a known sigma, and our n is greater or equal to 30. So our assumption is that we're going to use the z-distribution. Okay. So a lot of this will do the same way as we did with the rejection zone method, but we're doing the p-value. Okay. So now I always draw my pictures with these because the picture really can help. I'm not good at being an artist though. Okay, and our mu, I always do the mu line here, the mean in the middle, 40,000. Okay, now our alternative hypothesis inequality always points in the direction that we're interested in. Just right here. So what that means is we're going to be interested in this side of the tail. So I'm going to draw a line right here. And in the past, we would say this is the rejection zone, but we're just going to say this is the shaded area, which is on the other side of our critical value. So for this problem, our critical value, or our cutoff value, is the 2.5% level of significance, or it is also known as 0.025, which is 2.5%. Okay, that's our critical cutoff value, or critical value for the level of significance. Okay, so now all that we need to do is we need to do some calculating. And we're still going to do our calculating the same way that we did before. So x bar minus mu, and then sigma over little n. And I'm going to jump to the ending value because I don't want to elaborate on this part. But the z-score that we end up getting, this is what we call our calculated statistic. is 2.262. The last 2 is probably not as important, but 2.262. Okay, now we're solving this problem with the p-value method. So what we need to do is we need to figure out what this is equal to on our z-table as a probability under the curve. So I'm going to get out my table that I have here, and I'll zoom in a little bit. Okay, so our value was 2.26. It's because my table only goes out 2 digits, 2 decimal places. So 2.26. So we have 2.2. 2.26 is right there. Okay, so that's 0.4881. 0.4881. So we need to remember that, 0.4881. Okay, so that represents this area right here. And I'm going to back out the zoom just a little bit. Okay. But so that's 0.4881. We need to figure out what this area is that's shaded, because that's what we're interested in. We want to figure out if we're past 0.025, what the cutoff would be for that. So it's going to be 0.5 subtract 0.4881, and what that equals is 0.0119. So with the p-value method, what this means is right here. So what this means is this is a very rare event for what we're looking for. And what it means is we would be over here somewhere. We would be past our cutoff of 0.025 because this is smaller, 0.0119. So this is a more rare event than our cutoff level, which means we're okay with the amount of risk that we're wrong. Thus, we think that the null hypothesis might not be right, which means we're going to reject H0, which means plumbers may be making more than expected. And one way to remember this too is when your critical value is greater than your calculated value, you reject. Okay, so that's how we do that with doing it by hand with a table. Let's just take a look at the calculator real quick. Let's see, I have it minimized, the emulator. Okay. Make sure we're on the screen here. Okay. So in the calculator, what we're going to do, make sure that's on, clear, and we go to stat, go to the tests, and then we are doing a z-test. So we hit enter, and we are going to do stats. If we do data, we have to load up lists that we already have set up, but we're not doing that. So we do enter. We go down. So we put in our mu, and our mu is 40,000. Our sigma is 500. Our x bar is 40 200. Our N is 32. Okay, and then with this one, what we have to do is we have to select the direction of our inequality. And you know that because this right here that's flashing, this not equal, this cannot be, this is a range of choices for your alternative hypothesis, because your null hypothesis cannot have the not equal in it. So what we're going to do is pick the right one, and in this case the right one is this right here. It's pointing to the it's greater than, it's pointing to the right. So we're going to go over to this one, and then let's go down and hit calculate, and it gives us the answer of 0.023 . Oh, that's interesting. What did I do wrong? Ah, there we go. I think I had the not equal to selected. Scratch that from the record. Okay, so this is what we get on the calculator. Technically, the calculator's more accurate than our table, because our table, we're limited with trying to pick the right one that fits. And it only goes out to decimal places. Okay, so our p-value, this is what we have here. This kind of shows what some of the other variables that we're working with. 2.26, which is our z-value, which is accurate, so we know that we're matching what we're working with. And then our p-value is 0.0118. We got 0.0119, so we know that we're on track, and everything looks good. But like I said, this is slightly more accurate. Okay, and thank you for watching.